Well, how are you guys doing today? You know, it's a good day because you woke up. Right? It's always a good day when you wake up. Let's get on to some a little bit of review here today. We're going to be hitting solutions, and this is second semester general chemistry. So yeah, we did cover solutions in introductory chemistry, first semester general chemistry, but not in the depth we're going to be looking here in second semester. So I'll be mentioning some review material that I highly recommend if you've gotten a little dusty in the brain, got some cobwebs you need to blow out. You might want to head back to your textbook or watch some of my videos from first semester general chemistry on solutions, especially when we get into concentration later. We're going to introduce some new and very odd concentration units. Yay! But first, I want to start with the qualitative aspect of solution formation, and let's look at it based on the knowledge we have of intermolecular forces. Now we can apply these to solutions, because remember, and just as a quick review, a solution is a homogeneous mixture. So it's mixed evenly throughout. It's got consistent properties all the way throughout. And that contains at least two components, right? So main component is the solvent. That is the substance, and in the majority of cases, that's in the larger amount, right? You take salt, dissolve it in a pot of water. Water is your solvent. It's what's doing the dissolving, right? And that, pardon me, and that solvent is what determines the overall state in most cases of the solution itself. So if I've got water and I sprinkle some salt in it, the resulting homogeneous mixture is still a liquid because the solvent water was a liquid. So most of the time, and in most examples, we are dealing with liquid solutions, typically with a solvent water, which would be aqueous. That's why you see, a lot of times ions and ionic equations, you see Na plus AQ, because that means that is dissolved in water. Right on? But you can have other states of solutions, right? Gas, like air. Breathe in, breathe out, breathe in. You've got oxygen, nitrogen, you've got argon, you've got different things coming in. It's in the gas phase. When you breathe out, carbon dioxide, water vapor, right? Those are solutions in the gas phase. Right, evenly mixed throughout. That'd be a bummer if I'm breathing air and all the oxygen's on that side of the room, all the nitrogen's over here. Right? I just walked to that side of the room and I got oxygen. But if I light a match over there, my whole house catches on fire. Good thing it's mixed evenly throughout, right? And then a fun thing I talk about in prep chemistry, introductory chemistry, are alloys, which are literally solid solutions, right? You take, pewter, brass, bronze, you've got one type of metal. And we looked at metals. You could take, say, a copper matrix, copper lattice, and replace the copper atoms with other atoms of similar size, and you can alter its hardness, its melting point. You can get some, I mentioned titanium, vanadium alloys for hip replacements, things like that. You can change the structural strength of it. Really cool stuff. So alloys, some people spend their entire lifetime just looking at alloys, because look at the technological marketing of that, right? So trying to make structural material that's not going to crack or rust, and woo, I can do a whole video just on alloys. But anyway, just a quick review there. But we're going to focus in the beginning for this particular section on solutions on the qualitative aspects of solution formation in terms of intermolecular forces and energetics, but without the math to it, because we really haven't covered thermodynamics yet. We covered some thermochemistry earlier, so you'll understand terms of enthalpy and heat and things like that. But let's get to just some qualitative stuff and look at how solute and solvent particles on a molecular level interact, right? So if you need to review intermolecular forces, do so now. So if we're looking at solution formation energetics, we can really just think about it as you've got the solute and the solvent. Think of those as two separate things, right? And they have intermolecular forces of attraction. Could be ion-ion, could be hydrogen bonding, dipole-dipole, LDF, whatever it is. It's between like species, okay? And the strengths are different. Obviously, the stronger those forces, the harder it is to pull them apart. Well, would it make sense in order to mix the solvent with the solute, we'd have to break apart those particles? We'd have to separate the solvent and separate the solute particles, theoretically, right? So step one, we can look at this as three very fundamental steps. If we look at a very specific species, it may mix it up a little more, right? But fundamentally, follow with me. Let's take the solvent particles, whether they're water or octane or kerosene or ethanol or ammonia, doesn't matter what it is. And let's break all those intermolecular forces, right? So we have to break intermolecular forces to separate the solvent particles. So would it make sense? That would require energy because you're breaking those intermolecular forces. You're making room for the solute to come in, right? Yay. So that's going to be an endothermic process. Let's call that delta H1. It requires heat energy, right? So the enthalpy change would be positive in that. All right, wouldn't it make sense? We would, and then in order to get the solute particles mixed in with the solvent particles, we'd have to break all the solute particles apart. Well, they have intermolecular forces ranging from, relatively weak, London dispersion forces if they're small, strong ion-ion for ionic, etc. Well, to break those intermolecular forces is also going to require energy. That would be endothermic. So delta H2, the solute breaking apart process, would be endothermic. Now we've got the separated solvent particles, the separated solute particles. Let's mix them together, right? But now we're forming intermolecular forces. Those may be favorable if they're similar in size and have similar intermolecular forces, like they both hydrogen bond, they're both about the same size, or maybe they're both they're both nonpolar but about the same size, right? But if they're very different, one's hydrogen bonding and small and one's nonpolar and large, they don't even like each other, right? So you can see how these may be more favorable or less favorable, but in general, you're forming intermolecular forces, even if it's super, super weak, like dipole-induced dipole forces, polar with nonpolar. That can happen a little bit. So regardless of what's going to happen, we're going to mix the solute and solvent particles. You're forming intermolecular forces, so that's going to be an exothermic process. It may be a very tiny exothermic thing or a very large exothermic thing if they like each other. So you can see the combination of these, the overall process will just be delta H1 plus delta H2 plus delta H3. We'll look at that in 4 scenarios. And the 4 scenarios will cover, right, how big those are, the 2 positive endothermic steps, versus how big that negative exothermic step is. Because if this overwhelms those, you have an overall negative or exothermic process. If this is less than those, you have an overall positive or endothermic process. That gives you different types of solutions. So let's look at the 4 possible scenarios based on the types of intermolecular forces between the pure components, the solvent with itself and the solute with itself, and with the solute and solvent after they mix. That may be favorable or not so favorable. Case number 1 for our fundamental types of solutions based on the intermixing energetics, right? So in this case number 1, this is called an ideal solution, kind of like ideal gases. We can simplify the mathematics. So we're going to be focusing the majority of our cases when we look at solution properties later with ideal solutions in this, theoretical scenario. So what would an ideal solution be? And I'll draw a kind of a Hess's Law energy diagram on the next board so you can kind of see it mathematically. So the intermolecular forces between the solvent particles and the solute particles, right, are the same type. Maybe they're both London dispersion forces. They're both nonpolar. Maybe they can both hydrogen bond. Maybe they're just both polar. Those kinds of things, right? And roughly the similar strength, right? Same sizes, same amount of London dispersion forces. Essentially, if you put them in solution, they would think they were each other, right? They'd be like, oh, you look just like me, even though maybe slightly different, but I think you're me, woo! So the solute could be with itself or with the solvent, and it really doesn't make a big difference, right? So you'll see mixing, and it doesn't really change the energetics. You'll see this on the graph in a second here. This creates what I'll call a pure homogeneous mixture, a true solution, an ideal solution. And what's special about ideal solutions is the properties, which is what we're after later. We're going to spend a lot of time, a lot of videos on solution properties. The vapor pressure, osmosis, freezing point depression, boiling point elevation. We're going to get into all these things. For ideal solutions, we can actually predict changes in those properties of solutions based on the properties of the pure components, right, for an ideal solution. For the other 3 cases, we won't be able to do that. There would be some severe percent errors. So examples, two nonpolar species, so London dispersion forces only, and pretty much close to the same size, within a few carbons of each other, we would consider that in my class an ideal solution, right? Or maybe benzene and toluene. Benzene's that hexagon with the alternating single and double bonds. Toluene is the same thing with a CH3 sticking on the end. I mean, they look pretty much the same, right? For my class, water and methanol, maybe ethanol, right? Because hydrogen bonding, both pretty small. You know, if this rotates, water thinks methanol's water, methanol thinks water's methanol, right? We're going to consider that ideal. We good? Let's draw the graph on this to look at the energetics. Let's draw this Hess's Law diagram together. Remember, Hess's Law says if you can get to the same spot. If we start here and end here, it doesn't matter if we go 1 step, 3 steps, 2 steps. Kind of like, these are like simplified Born-Haber diagrams we did when we looked at ionic compounds and lattice energy. All right, so let's put enthalpy on this side. Think of it as energy, but enthalpy, or heat. Right? Let's call it enthalpy. Let's start with the separated, gotta keep them separated, the solute and the solvent by themselves, right? So here's the starting energy point, or enthalpy point. So remember the first step, we need to break apart the solvent. That's positive, right? So let's go up and let's separate the solvent. And let's call this delta H1. So in this case, we've got the solute plus the separated solvent. All right, so individual solute, individual solvent. Up here, we haven't done anything to solute yet, but we've broken up the solvent. That's the energy, the enthalpy it takes for that one. And we know it's endothermic, so it goes up. Now let's do the same thing to the solute. So that is also endothermic. So this would be delta H2. And we know that's endothermic because we're breaking the intermolecular forces. Oh, I fumbled. So this will be the separated solute plus the separated solvent. So far, so good. And then now that they're both separated, it took energy. We're tired. But it's like, riding a bike up a hill. And then you get to the top, you're like, yay! Coast all the way down. I do that with my little kids when they were babies. I had a little baby thing in the front of the bike. Strap them in there, and they're like, I had the little sun hat on and whatever. Sometimes the sunglasses, they're binky. And I'd be like, and your legs, your knees are way out because you got the baby thing in the way. You're like, and I get to the top of this hill. We'd be checking out, the cool homes and stuff. And we get to the top of the hill, and then we start coasting down. And they're like, and then their hat's blowing. And when they were old enough to talk, I go, cruising. We go, cruise, daddy, cruise. When they're babies, they just were like, drool flying. Good stuff going downhill. It's great, isn't it? So once they're separated, we can go downhill. Yay! But what's interesting for an ideal solution, remember, the solute thinks the solvent is itself, so the energetics completely cancel out. And you end up where you started, right? So let's look at the overall energetics of this, right? Hess's law says, well, we can just add these all together. We'll call that delta H solution, the overall enthalpy change of forming the solution. Well, that would be just delta H1 plus delta H2 plus delta H3. You just add them all together. The energy it takes to separate the solute, the solvent, the energy it takes to separate the solute, and then recombining, breaking intermolecular forces, forming intermolecular forces. Turns out they're all the same in this case. Whoops! And for an ideal solution, that is 0. And you form a pure homogeneous mixture with properties that can be predicted from the pure components. Yay! This will be our main focus, so put a star next to that one. We're going for it. Now, let's take a look at the other 3 scenarios, which will be Well, what if it goes down, further? Oh, so you end up lower than you started with, or higher than you started with. Then you think, well, that would only be 3 cases, but there's 4. So we're going to look at lower, just a little bit higher, and then way up here, right? And you're like, hugely endothermic overall process. Let's look at the next one. Case number 2, my friends. Well, if the other one was an ideal solution, this would be a non-ideal solution, all right? But there's going to be 2 cases of non-ideal solutions. The first one is exothermic. The next one will be non-ideal, but endothermic, all right? So in this case, the solvent and solute particles, they have intermolecular forces with themselves, but they're actually more favorable with each other. The solute would rather be with the solvent. It's more preferable intermolecular forces with the solvent than it is with itself. See that? So the overall process would be less than 0, and I'll show you that energetically here. The problem with non-ideal solutions, that's why they're non-ideal, you won't be able to predict the solution properties from the properties of the pure components. So it doesn't do us any good at this level. So we're going to be stuck with using ideal solutions. We're fairly limited in our examples later on down the road. It's still a homogeneous mixture, though. If you look at it, it would look homogeneous to you. It's a solution. Okay? So let's look at an example and how the intermolecular forces play in there, and then we'll look at that diagram, the energetics diagram, the enthalpy diagram. All right, let's look at an example of this case. Let's take dichloromethane, at least for my class. Dichloromethane, CH2Cl2. So again, you'd have to draw the Lewis structure, Vesper structure, look at bond polarity, see if it's polar, nonpolar, all that fun stuff from last semester. Make sure you review that. And then acetone, right? CH3CO, it's got a double bond there, CH3. So let's draw these, right? So let's draw. So carbon's going to have 4 bonds in this scenario. So dichloromethane will have a tetrahedral shape. I'm going to rotate the tetrahedron to show you how it goes with the acetone in a second. So let's draw that carbon. Let's draw kind of a sideways tetrahedron. Like that. Normally I would do it, flip it this way, but you'll see what I mean when I do this later. Now, would you agree that you're going to have the more electronegative species over here? So you're going to have the partial negative, partial positive over on this side. So that is a polar species. So that has dipole-dipole forces, right? I skipped a lot of steps there. Now let's take a look at the acetone. The acetone is going to have a carbon bonded to a carbon with a single bond, double bond. So that's 3 electron groups. That's going to be trigonal planar. So let's draw acetone. And I'm going to rotate it because the oxygen is the more electronegative atom. That's the partial negative side. So I'm going to rotate it so the oxygen's here. Let's draw it like this. With the carbon. And here's your CH3. Does this give you bad memories? Hopefully good memories. So there's my tetrahedron, 120-degree bond angles. So there's what acetone will look like as far as a Vesper or dash wedge structure. Well, obviously, here's your partial positive side, partial negative side, right? Very highly electronegative oxygen. You've got this partially positive hydrogen, and it's really tiny. It's almost like a hydrogen bond. Not quite, but it's like right. If hydrogen bonding's here, this is like really close, right? So you're going to form this intermolecular force of attraction. And this, if you look at itself, would have dipole-dipole forces. Because that's polar. So acetone with itself is polar. It has dipole-dipole forces. Dichloromethane with itself is polar, has dipole-dipole forces. With each other, these are dipole-dipole forces on the edge of hydrogen bonding. You see that? Some people would even consider that a hydrogen bond. For my class, that doesn't quite qualify, theoretically. But can you see how the dichloromethane would be more attracted because the oxygen is more electronegative than the chlorine there? It's more attracted to that, to acetone, than it is to itself, right? So this would also be considered dipole-dipole plus London dispersion. Right, this would add LDF, LDF, all this is, well, we'd have to look at the molar masses and whatnot. But in essence, they have similar intermolecular forces, slightly different sizes, but hopefully you agree with me, in this case, dichloromethane would rather be with acetone than with itself. So that's going to be a more favorable process. So when we draw that on the diagram, delta H3 is going to drop lower than delta H1 and 2 go up. Let's draw that. So you're going to be doing quite a bit of this. Some of you can do that in your head. Some of you might need to draw this to go, well, does the solvent, would it rather be with itself or with the solute? You'd have to look at the Vesper structures and look at the polarities of them. So what I did for the energy diagram for this non-ideal solution is it starts exactly like we did with the other. They all start the same. Now, these values may vary in size. We're not looking at actual quantitative values at this point, but you get the general idea. So take the separated solute and solvent, break up the solvent, endothermic, break up the solute, endothermic, you end up way up here. Now we get to go cruising down the hill with our hats flopping. And what's going to happen, because in this case the solute would rather be with the solvent, right? It's more favorable, so this is going to drop. Ooh, that would end there for an ideal solution if they're exactly the same, but in this case, it actually drops slightly below. So let's carry this out here. Now do you see the difference between the starting point and the ending point? Well, this is your delta H solution. That's the enthalpy change of forming that solution. And Hess's law says, let's label this one. So this is our solution here. Delta H solution going from the start to the finish should be the same as that plus that plus that, because you end up at the same place. Yay, Hess's law. Okay, and so this will be less than 0, right? So this would be exothermic. So we ended at the same spot with the last one. And again, delta H solution is just the sum, says Hess, of the three processes. You could probably do the next one. So case 3 is going to be almost identical, but we're not going to end up down here. We're going to end up slightly up here. It's going to be slightly endothermic, right? Still end up being a homogeneous solution, but it's going to be a non-ideal solution. But case 3 will be slightly endothermic, where the solute and solvent are slightly more attracted to themselves than to each other. So it really doesn't want to mix as much. There will be some mixing, but it's not as favorable. Let's look at the next case. Case 3, also non-ideal, but this case it's slightly endothermic, not slightly exothermic, meaning the solute and solvent like to be with themselves more so than with each other, even though there will be some intermolecular forces of attraction. I'm going to see if you can do that yourself. Right? So delta H solution will be a little bit greater than 0, so slightly endothermic, therefore non-ideal, meaning, like the last case, we won't be able to predict the properties of the resulting homogeneous mixture. And this will form a homogeneous mixture. Still forms a homogeneous, so it looks like a solution. But the properties of solution will not be able to be predicted from the pure components, the solvent and solute themselves. So an example, let's take carbon disulfide, or like any nonpolar molecule, right? And let's do a slight spin-off of the acetone. Let's do diethyl ether in this case, right? Which is slightly polar, but it's a little bit larger. I'm going to do this on the next board. I'm going to draw it up for you, but see if you can do it yourself. Do the Vesper structure for that, the Vesper structure for that. What are the intermolecular forces between carbon disulfide molecules themselves? What are intermolecular forces between the diethyl ether molecules themselves? And look at when you put them together, why would they not be they can interact, and what would be the intermolecular forces of attraction between them, but not as favorable as with themselves. Give that a shot. Let's see if you can get this process. So here's carbon disulfide, right? Nonpolar, London dispersion forces only, so the bond dipoles will cancel out there. The diethyl ether, of course, is going to be slightly polar. It's larger, so it's got stronger London dispersion forces, but it's got that little polar section here with that oxygen, so it's going to have these weak dipole-dipole forces here. Partial positive on that side, partial negative on this side. And you could rotate this around and get the same net result. So what's going to happen, if you remember from intermolecular forces, you've got a permanent dipole here, right? Nonpolar, but this is polarizable, right? So the electron cloud of the carbon disulfide is going to be shifted. It's going to see this partial negative side, or if you flipped it, be attracted to the partial positive, and it's going to push electrons over. Let's do that in red. You're going to see that electron cloud morph, and it's going to induce a dipole. So you're going to end up with dipole-induced dipole forces. Remember that, my friends? So we'll get this carbon disulfide here. Technically, you don't need those lone pairs on the Vesper structure, right? But we're going to create this induced dipole, right? That's going to push electrons over, and that's going to be attracted. That's a pretty ugly straight line. I cheated on my CH2, CH3. Can you see? I didn't want to draw those tetrahedrons. You'll see that commonly in organic. You're like, it really doesn't matter. The focus is here, right? So I'm going to cheat on my CH2. I still have the trigonal planar, though. You can still see the 120-degree bond angles on that central carbon. And so we got the partial negative here, partial positive there. And these are our wonderful dipole-induced dipole forces. But since it's induced, this is nonpolar, that's polar. They can attract to each other, so they'd be slightly soluble, but they would still rather be with themselves, right? So in this scenario, delta H overall is slightly endothermic. So we've got a non-ideal homogeneous mixture or solution. All right, we got one more case where we've got non-polar, but really non-polar, and really polar, not liking each other one bit. You'll still get some dipole-induced dipole forces, but just minor amounts to the point where you wouldn't be able to tell, and it doesn't look like those two species mix at all. You've probably seen this last case in your everyday life, right? It's called a heterogeneous mixture. Heterogeneous means you can see the two different components. It's not evenly mixed. So the intermolecular force type and strength are so radically different between the solution and the solvent particles, they really don't want much of anything to do with each other. The solvent wants to stay with its buddies, and the solute wants to stay with its buddies. No mixing in. I mean, there might be a small amount of mixing in between, a slight amount of dipole-induced dipole forces, but you probably got a really large nonpolar species with strong London dispersion forces, with maybe a really small, highly polar, maybe hydrogen bonding species like water with some large hydrocarbon or something like that, like gasoline. Gasoline and water don't mix, right? Oil, you get oil or grease on you, water just rolls right off off a duck's back, like a freshly waxed car. They don't mix with each other, right? So highly polar, highly nonpolar. In this case, the delta H solution is going to be really, really highly endothermic, right? Case 3, it was just slightly endothermic, so you get enough mixing to form a homogeneous mixture. But in this case, the mixing amount is so minute, it wouldn't be visible to our pathetic human eyeballs, and you would look like you would get two layers with a less dense layer on top. If that happens to be two liquids, like gasoline is less dense than water, so you'd see a water layer and a gasoline layer just floating on top. So gasoline spills or oil spills in the oceans are just horrific because the oil's less dense and it just spreads out across that surface and forms this layer. Environmental messes, big time. It's horrible. But then think of the other way. What if it was more dense? The oil would just go, bleh, but it wouldn't spread out like that. It would just sink. I wouldn't want to be under that giant oil spill as it's sinking. You know what I mean? But it is less dense, so it's a moot point. It stays on the top. So the solvent and solute stay mostly separated, forming visible layers. Now, if they're both liquid, if solute and solvent are both liquid, you'll see two liquid layers. Again, the less dense one on top. We call that immiscible. Those liquids are immiscible. They do not mix. Let's look at the energetics. Hopefully you took the initiative and did this before I did, right? So let's start with the separated solute, the pure solvent, not mixed. Let's break up the solvent molecules. Requires breaking intermolecular forces, so that's endothermic. And then let's separate the solute particles, endothermic, moving up. Now we're at the top. Now we can mix them, but these ones don't want to mix, right? You're going to get a slight amount of induced dipole forces, so it'll be slightly exothermic, but it's not going to drop down very far, right? Case 3, it dropped down pretty close to where you started, but in this case, it does not drop down very far. So we've got the mixture here. I'm not even going to call that a solution, right? Because the solution would be a homogeneous mixture. This is heterogeneous. And so if we look at this difference here, that's your delta H solution. This is, again, snore, snooze, fest, delta H1 plus delta H2 plus delta H3. But that's highly, highly endothermic. So not favorable in the slightest. So it's a lot greater than 0. Right? And examples would be, like I said, something very small. Right? Let's do this in green. Let's take water. Actually, I'll draw this out. Let's take water. Looks like the Mickey Mouse, right? So we got the partial negative, partial positive. So it's got the polar. It's got the hydrogen bonding, right? You can see the strong hydrogen bonding, very small, weak LDF forces. But let's say we want to mix this with some large nonpolar species. For example, let's take, you could probably just do benzene, or we could do toluene, right? Or put a couple CH3 groups. So it's really large, very nonpolar. LDF only. They don't want much of anything to do with each other. Now, this could induce a slight, induced a slight dipole on it, but we're hardly going to get any mixing. So I'm not even going to draw the net effect. I guess you could draw like we did in the last one, right? The induced dipole on there, but it's so little, they just don't mix. So if this is less dense than water, that layer would just float on top, right? You got it? We'll do in another video a specific example. We'll do like an ionic solid, which is where I'm probably comfortable with. I might put some numbers to it, but we'll look at a specific scenario where we'll look at specific delta H1s, 2s, and 3s. All right, so you got the basics here.